All right then, ladies and gentlemen, moms and dads, boys and girls, it's time for our last subject, the one that will take most of the week. And that is basic electricity. All right. So that's where you're going to be heading after this class into AMT 300 and 301, which is all electricity. And electricity is actually quite simple. The hard part for most people going to A&P school is you can't see electricity. You can feel it if it helps. I'll let you feel it. I had a group of fine young students today came through the hangar, and I let them feel a couple thousand volts and played with actually a couple thousand amps too. So nobody died. Only a few people said ouch. So, but it's just a concept. You just have to I don't know, either believe it or don't believe it, but understand it and follow it. So to understand electricity, I guess we should understand what is it actually besides, well, in short, it's smoke. It's magic smoke. And they put the magic smoke into the machine. And if you let the magic smoke out of the machine, it doesn't work anymore. And that's kind of what it happens. So what is electricity? Well, to talk about electricity, we got to get all the way down to the atomic level. We got to talk about atoms at a very basic level. And I do believe one of your Q&A questions asks you something about this, and the answer is the atom is considered to be the most basic building block of all matter. All right, so we're going to build a very simple little atom with a very simple way. That's one thing I like about the FA. They kind of keep some things simple where it needs to be. If we were to really study the atom and get down to what it really looks like, you get into probabilities of where things are located and probability locations. Or if you get not quite as complicated, what was that show? Every time I get it, I go, what was that show? I should put it up on the slide. Big Bang Theory. Every time they changed the little scene, they had a little atom with a little electrons flowing around it. That would be even a 3D model. But we're going to use a 2D model because that's what the FA does. So using a 2D model of an atom, we have in the middle the nucleus. The B, the nucleus. That's the chewy nougat center of everything. It is the center of the atom. Center of the atom. I should have moved this over. Let's see. So I can go here. All right, center of the atom. Nucleus is the center of the atom. It contains some stuff. It contains protons and neutrons, or protons and neutrons. So let's see, protons. It's got some protons in there. We'll get proton. We'll make it with red and a little plus. And we got some neutrons in there. We'll make them little circles. So protons have a positive charge. And neutrons have a what? Neutral charge. There's Switzerland in there. They don't know. They don't care. So we got protons and neutrons. And for the most part, you have an equal amount of protons and an equal amount of neutrons. So if I have 2 protons, I got 2 neutrons. If I got 3 protons, I got 3 neutrons. They tend to stay balanced like that. And then floating around, we have electrons. Electrons orbit the nucleus. in shells. This is where it becomes a very 2D simplistic model. And I kind of stress that, so if you went out and go, oh man, this guy teaching AMT school, he's teaching us like this, and somebody who really does this stuff or takes it at college level go, yeah, that's not really accurate. So this is, just so you know that, but it works. So here we have this little dotted line represents the orbit of how these little electrons go. And we'll make our electron little like that. There, you have to stay. There, stay. So we have a electron, which has a negative charge. And you'll notice there's two of them, because if you have two protons and you have two neutrons, you most likely have two electrons. If you don't, then you have an ion, either positively or negatively charged. But for now, we just do that. So you have two protons, two neutrons, and two electrons. And if you knew your periodic table of elements, you would know that I just made helium. That's not important. All right. I can write this. So, now if the number of electrons I should put what charge do electrons have? Negative. I should probably write that next. Number of electrons, let's see, where am I? If the number of electrons equals number of protons. Number of protons, the atom is neutral. I don't know if they say that, it just isn't. But an extra electron. Now if I have one more electron than I do protons, I have more positive or more negative? Negative. So that's a negatively charged ion. And same can be true, an extra proton. An extra proton is a positively charged ion. Need to write this here. Electrons have a negative charge. Want to hear something that sucks? So yesterday was Father's Day. I had a good time with my oldest son at Stanford. I come home, and my middle son, they had it on Fortnite. And there's Hank Hill standing there. He goes, Dad, check it out, man. They got a new skin. And I love King of the Hill. I go, yeah, it's pretty sweet. He goes, it's you. Dang it, Bobby. His name's Emilio. So. And that was my Father's Day thing. You look like Hank Hill. I got the Hank Hill tan going. Electrons are very fast. They move at about the speed of light. Which is 186,000 miles per second. Miles per second. I would not make you memorize such a fact, but there you go. That's how fast they move. All right, so I tell you that to tell you this. There's the atom. It's got electrons. Electrons are circling around the atom. In reality, they're buzzing about, but we're going to say they circle kind of like a planetary system, like, you know, like the sun rotates around the Earth. See, it doesn't. So. Yeah, I'm testing it. Depending on how many electrons, there are in the atom, of course, there are and how they are arranged, and how they are arranged will determine if the atom makes an insulator or conductor. What's the difference between insulator and conductor? A conductor will allow movement of electrons. And an insulator will prohibit movement of electrons. So what's going on here is we have all of these, and I got to draw them smaller. So let's say we have a piece of wire. Here's a piece of wire. A wire happens to be a conductor. It's made out of copper. And I'm going to enlarge it real big there. So through the power of electron microscope, we're going to make that larger right there. And within there, we have all these atoms in there. All these little atoms in there. Let's make it really small. They're making up this copper wire. And then around all of those atoms, we have negative charge. So we have all of these negative charge. Negative charge is what? Electrons. And if we have a piece of copper wire and we lay it down and we touch it, we don't get shocked, do we? But there are electrons in there and they're all moving around, but we don't get shocked. But if we take this, we hook it up to a battery. This is a symbol for a battery. That's a positive plate. That's a negative plate. Positive plate, negative. That means it's a multi-cell battery, and I do this. What happens is we have this side of the battery is negative and this side of the battery is positive. Well, in the atom world, opposites attract and like repel. So that means the negative repels a negative. In fact, if we were to take an electron and we were to make it the size of a pea, and we made another one the size of the pea, their charges would be so powerful that it could move cars out of its way, sideways. It's tons of force they would produce. I don't know who figured that out, but somebody did. So inside, so we have opposites attract, likes repel. I'll come back to that in a second. So that means that we go back to our little atom, and we have a positive and a positive, and we had some, green, some neutral, and then we have our electrons floating around in there. Electrons, they want to attract to each other or repel each other? I just told you. They repel. But the protons, for some reason, don't seem to mind each other so much. They don't have as much power, so they're kind of happy in that little center. But the positive and the negative here, they want to attract each other. But much like a toddler on crack, that's probably a bad thing to say, these electrons have so much energy that they just buzz around. I should not say toddler on crack. I should say after a toddler who just ate an entire birthday cake and had a soda, 2 liter. They are going to buzz about like crazy, and the mom is the positive. Dad, of course, has to be neutral, Switzerland. I don't know what's happening. That's how I parent. You need to deal with that. And so the children have all this energy, but yet they don't leave mom. They sort of orbit around mom in this buzz, and that's an electron for you. So electricity is the movement of toddlers. And they have too much energy to be attracted in and stick to mom. So that's why they don't stick. But because there is this attraction, they don't wander off into target, the oblivion. So we have this going on. So we made a battery here. And the battery has got a negative here and all these negatives. So if opposites attract, battery has on this plate an excess of negative electrons. So it has this power of negative electrons. So we got negative, 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 comes all the way around. We'll kind of look at here. What happens when we have a negative right here? What does it do to this one here? Well, it wants to push it that way, and that one wants to push that one, and that one pushes that one. They hate each other, so pushing, pushing, pushing. And we can kind of think about it the other way too. Over here we have a positive. Well, positives that attract or repel? Attracts. So it starts, if you will, kind of pulling the electrons this way and pulls them right up into this way. So electricity is the flow of electrons. Is the flow of electrons from negative to positive. They go from where? Negative around to positive. That is called electron flow theory. But conventional, C-O-N-V-E-N-T-I-O-N, conventional theory is flow is from positive to negative. So believe it or not, it wasn't until like the 50s or something where they just assumed electricity was from positive to negative. And then they figured out, well, not that long ago, hey, wait a minute, it really goes the other way around. So does it matter?
No.
Not a whole lot. Nope. It just depends on how you look at it. And quite honestly, everything we do in the program, if you think of electricity as moving from positive to negative, the conventional theory, it's easier. Schematics are easier to read. Solid state diodes, transistors, they're easier to understand. They're labeled in such a way and drawn in such a way that if you look at it in conventional theory, it all makes perfect sense. If you look at it from conventional theory, it becomes very difficult to actually even follow diagrams, because in conventional theory, when something is actually a schematic, well, that's for another class. I'll tell you. So to draw a schematic, it's usually like this. That represents a ground, and then you would come off to a circuit breaker and a switch, and that switch is going to go off into something else. Maybe we'll have, a light here and another light here. These are lights, by the way. That's a schematic for light. And I have a ground symbol here. A ground symbol, when drawn nicely, looks like this. There you go. And so there, I got a light here. That goes to a ground. And so this is a circuit breaker, a switch. So that would be like how to turn on the navigation lights for an airplane. You'd have a red, green, and white. It's simple, but that's really what it looks like. And if I had to troubleshoot this, I go, okay, so I'm going to trace the wire, but I'm going to trace the wire using electron theory flow. And mind you, you would have maybe 100 other wires in this paper. You'd come out and go, okay, it comes out of the negative and goes, oh my God, I'm going to be here 10 minutes trying to find the next nav light. It's faster to go, no, it travels this way, through a circuit breaker, through a switch that's currently open, but if it's closed, and then branches off into the three lights, comes to lights, goes to a ground. Yeah, I know the ground's going to eventually end up back over here. I know it's kind of fast, but it's just to say that it's so much faster, easier, and better when you look at things from conventional, but you have to know the two theories and which one is which. So, all right, so we talked about what makes the electrons flow is, well, we have to have some sort of electron force, which in this case is a battery, and it forces electrons to go through. And I had mentioned that the makeup of the electron determines whether or not it is an insulator or a conductor. And an insulator, well, you know this, but it's worth pointing out. This is plugged into the wall. This on the outside is a insulator, because I'm not like screaming and saying, "Oh, that hurts," and stuck to it. Inside is a conductor, and sometimes it's kind of funny to me to think the only difference between living and dying is how electrons are arranged in an atom. And that's the truth. So, all right, I did all that. I did that. Yeah, I did that too. Two types of electrons. Okay. So, 3 types of electrical properties. 3 electrical properties. Electrical properties. Conductor. I feel like before I do that, since I'm not following my notes real well, I should do this. Let's talk about these. Here we go. Atom. We have the electrons orbit in things called what? Shells. Okay. And depending on how the atom is made up, will determine what it is. So I got a shell 1, now we got shell 2 over here. So shell 1 has 2 electrons. I made a shell with 4 electrons. And we can have another shell. And let's talk about what are some really good conductors. Oh, before I talk about conductors. How many electrons can you put in an orbit? So how many electrons can fit in a shell?
Up to 8.
All right, there's a formula. It's 2n squared, where n is the shell. So my shell 1, so 2 times 1 squared, that's what that is, will tell me how many, shell 1 equals. So how many electrons will fit in the first shell? Well, 1 times 1 is 1, times 2 is 2. Okay, so shell number 2 is going to be 2 times 2 squared, which is 2 times 2 is 4, times 2 is 8. Shell number 3 is 2 times 3 squared, which is 3 squared is 9, times 2 is 18, 4, you get the idea. 4 squared is 16, times 2 is 32. Okay, so it keeps going on and on like that. So I already told you that electricity is the flow of electrons. Well, the further out from the mothership the electrons get, the more easily they will fly off and go to the next electron next to them, go to the next, which then creates flow of electrons, which is electricity, or the flow of electrons. All right, so going back to our toddler analogy, I guess as they wander away from mom, they're more apt to find a guy selling candy out of his van. This is very dark, isn't it? It's just coming to me as I go. I don't know. I do have a big white van, but it's not one of the panel. It's got lots of seats in it. So as these electrons get further and further out, they're more apt to leave the mothership, the nucleus, and wander off. So they make better conductors. And so if we talk about what are some of the really good conductors of electricity, well, you already know. What are some really good conductors of electricity? Give me one. What does everybody have in your house? Copper. So a copper electron has 29 electrons. And they are arranged, so the first shell can have how many?
2.
2, and it does. The first shell has 2. The second shell can have 8, and it does. The next shell can have 18, and it I did that backwards. You don't know that. I do. 18, and it does. And that leaves 1 left over, so there is 1 out in the 4th shell. And that last shell is called the valence ring or valence shell. So that's pretty good. It only has one, and it's way out there. We'll talk about why one is good. What's another good one? Gold. Gold has 79 electrons. It is, let me see, gold 79. 2, 8, 18, 32, back to 18, and 1. Silver is another one, has 47, and it is 2, 8, 18, 18, and 1. All right, now I can come back up to here. Electrical properties. A conductor. A conductor is defined by something that has less than 1/2 of the allowable valence electrons. So if we go back to copper and look at copper, we're all the way out into the fourth shell. Fourth shell can have 32, and it only has, is that less than half?
Yeah.
Makes it a good conductor. Gold, 79. Last ring has 1, 2, 3, 4, 5, 6. I don't want to do the math, but I can sure to say 1 is less than half. 1 is less than half. So those make good conductors. So conductor has 1/2 of the allowable valence electrons. Remember, valence is the outer shell, last ring. All right. 2, we could have an insulator. I don't have a bunch of examples like I did there. An insulator has more than 1/2 of the allowable valence electrons. What are some good examples of insulators? Rubber. Wood. Glass. Very important one that we use a lot in aviation. Air. It's actually the standard. So air is an insulator. But speaking of air, anything can be a conductor if you put enough voltage through it. You ever seen electricity travel through air? Of course, we've all seen lightning. So that's just, you put enough voltage through anything, it becomes eventually an insulator. So, okay, so why are they insulators? Because they have more than half the valence electrons, so they're all still kind of closely held. It doesn't like to give them off. They really want to stay close to the mothership because they got the little family unit going on there and they're happy. So the guy with the van and the free candy doesn't, there's always one to grab. Hey, that's just, no, you can't go for the free candy. Let me see. At the point where the material, whether it be rubber, wood, glass, air, plastic, gives off electrons. It is said to break down or having broken down. Breakdown. It had a breakdown. Well, that's gave it too much. All right, so I said there are 3. That insulator, conductor, and semiconductor. Is it an insulator or a conductor? It's a conductor, but semi a conductor. Not a great one. So it's in between the two. In between conductor and insulator. Closer to conductor. And we'll talk about that in another class. For now, we'll focus on insulators and conductors, and more on the conductor than the insulator. All right, you guys gonna be good for another half hour? Okay. All right. So that's what makes electricity. What is electricity? The flow of electrons. And those electrons flow from negative to positive. What's in the middle? Nucleus. What's inside the nucleus? Protons and neutrons. Neutrons have a neutral charge. Protons have a positive charge. Why are they negative and why are they positive? I think they just made that up and just said, well, it's a charge. Let's call it negative. And that's a charge. Let's call it positive. It's just the way it went. Just like, how did it flow? I'm like, well, actually it flows the other way. We don't know. So we're going to talk about units of electricity now. All right, we have three things we have to be concerned about. Four things. There. That's electricity explained in a nutshell. You have three things: volts, amps, and resistance. Voltage is the pressure that pushes the amp. The amp is the actual flowing of electrons, and the ohms is the resistance. So when we talk about an electron moving and going, it's like water flowing through a pipe. And you could actually count how much water goes through a pipe, just like you could count how many electrons just past a certain point, how many electrons are flowing. And then we'd call that amperage, if we count how many electrons are flowing. And voltage is pressure, how much is being pushed. It's a difference of two things. So that is measured in voltage, and resistance is measured in resistance. Wait, what comes after that? I'm curious. Nothing good. Okay. We'll get to that after lunch. Units of electricity. All right, so let's start with current. So, current. Like in a river, you have a thing called current. It's the movement of the water. So current. And okay, so some of the hard part about electricity is we're going to talk in code, so people who don't understand electricity have no idea what we're saying, so we can charge more. So current. So the symbol is I, because it's current. We have to have a symbol for I. So it's I, which stands for intensity, but we'll never use that. Symbol is I, stands for intensity. It is measured in amps or amperes. Actually, it's named after Andre Marie Ampere. Andre Marie Ampere. There, now I said it right. Ampere. And because it was named after Ampere, it's always capitalized because it's actually his last name. So if we said we had 5 amps, we would say 5 amps, tall A, because we're paying some respect here. 1, 2. It is the flow. It is the flow of electrons through a conductor. Like water moving. Use a lot of water analogies. I try not to as much as possible because some people are like, hey, one time I wanted to go take golf lessons, and I eventually did. This is a story for you. And so I go to take golf lessons, and the guy could not stop equating it to baseball. And I'm like, okay, I suck at baseball, and so I'm going to suck at this sport if you're going to keep trying to tell me how to play golf based on baseball. It's not going to work. So if I try to explain electricity as though you're a plumber, you're not a plumber, you'll never get it. So I try to be cool about it. But everybody, most of you in here, use the bathroom sink. So, there's a certain amount of familiarity. Let's see. 1 amp, 1 ampere, 1 amp is the rate of flow of 1 coulomb per second. And you're thinking, of course it is. Now I get it. And what's a coulomb?
Charge.
It's 6.28. Interestingly enough, 6.28 happens to be pi times 2 times 10 to the 18th power of electrons. You should memorize that for the test. I'm absolutely kidding. That would be a ridiculous thing. Why would I have you memorize that?
You said 18th power?
10 to the 18th power, yes. That's cool.
I remember that.
But I have to tell you what an amp is. Otherwise, somebody say, well, you didn't tell them what an amp is. Well, yeah, I did. All right, so current, that is the movement of electrons. Then we have voltage. And the symbol is E, because V would be stupid. E, and I believe that is for electromotive force. Some people say, just for fun, electron, E-L-E-C-T-R-O-N, electron moving force. Doesn't really mean that, but it works. All right, electromotive force. It is measured in volts. That's good. Named after Alessandro Volta. So we use the big V. It is electrical pressure. Electrical pressure. And I will say this 100 times, and I will say it with emphasis. The more I say it, the more I emphasize it, the more you'll understand it. It's like speaking louder and slower in your language to somebody who doesn't speak your language. Oh, certainly if I speak louder, slower, and louder. So forgive me for that one. But it is a difference in potential. And by that, it's like when we measure pressure, air pressure, like air pressure in your tires, right? You're supposed to have air pressure in your tires. So, say we're supposed to have 40 psi. That's 40 pounds per square inch. It's the difference of potential really between what's in the tire and what's outside of the tire. When you use a tire gauge, it's actually referencing the outside air versus what you're measuring in the tire. That's how it's calibrated. So pressure, psi, it's a difference in potential, just like voltage is. You have to have 2 probes. One probe is like the low side, one side's the high side, for lack of a better term. So if I had a battery, like the battery in your car, I have to draw a battery because, you don't know what I'm talking about. Have the positive and negative side. And I take a voltmeter, because a voltmeter has 2 wires. It has a black wire, it has a red wire. And if I put the black wire over here, and I put the red wire over here, it's going to say 12. Because there's a difference of potential between this side and that side. But if I take the black wire and I put it over here, it's going to say 0. Because there's no difference between the two. It's the same. Just like if you took a tire gauge, you put it inside the tire, tried to read it. That little window. It says 0 in there because it doesn't have an outside reference. So you got to have a difference of potential there. a difference of potential. And now you get it, right? Okay. So voltage. Symbol is E, measured in volts. Okay. I did take this class, and they use V instead of E, and it was like threw me off because I've been teaching it this way for so long. So I guess the new convention must be V, but I like E. Resistance. Resistance. The symbol is R for resistance. Because why wouldn't you? Because that just makes it easy. R, symbol's R for resistance. It is measured in ohms. Ohms, that's not apostrophe S, it's ohms. Measured in ohms. Measured in ohms. Named after, I guess that'd be Horace Simon Ohm. So we use the big O, and it's got this one of these. And it's a Lululemon. Some people get that, some people don't. If you get that joke, it just means you pay too much for your clothes. It restricts the flow of current and causes a drop in voltage. It is electrical friction. All right. And that brings me up to that point.